In traditional software engineering, a programmer's role is to write explicit, hard-coded instructions. You define the rules, and the computer applies those rules to data to produce a result. But this approach hits a ceiling when the problem is too complex for static rules. A human can't manually code every visual variable required to identify a face, or every market fluctuation required to predict a price. Machine learning swaps the inputs. Instead of feeding the computer rules, you feed it the raw data and the desired results, the labels. The system then works backward to infer the mathematical relationships that connect them. Because the computer derives these relationships itself, the final product of the process is not a single answer. It is the set of instructions, the model, that will be used to solve the task for all future data. In 1997, Tom Mitchell established a formal definition for this process that remains the industry standard. He defined it through 3 variables. A computer program is said to learn from experience, E, with respect to a specific task, T. The third variable is the performance measure, P. For a system to truly learn, its ability to perform task T must numerically improve as it is exposed to more experience E, as measured by P. To see how this works in a production environment, we must map the pipeline that translates raw, real-world experience into a predictive mathematical model. Under this definition, machine learning is a rigorous, structured pipeline of quantitative translation. Raw data in its native state is useless to an algorithm. For a machine to process a phenomenon, that phenomenon must be translated into a mathematical format. This chart outlines the standard data pipeline. It begins with measurement, gathering data from sensors, cameras, or databases, and moves through a series of transformations toward a final prediction. Pre-processing is the first major hurdle. This is where noise is filtered out and the data is normalized, ensuring the inputs are clean and consistent enough for the system to analyze. Consider a spam filter. To the computer, the text of an email is just a string of characters. It has no inherent meaning. The pipeline extracts specific traits, like the sender's IP address, the email length, or the frequency of certain words, and organizes them into a feature vector. This is an n-dimensional array of numbers that represents the email in a coordinate space. The algorithm never sees a message or a picture. It only sees reality as a quantified array of features. As this workflow shows, the process is divided into 2 distinct phases. There is the phase where we build the engine and the phase where we run it. In the training phase, we provide the algorithm with both the feature vectors and their verified labels, the ground truth. The algorithm uses this paired data to find the patterns that distinguish spam from ham. The prediction phase is where the system is deployed. It is given a new, unlabeled feature vector, and it uses the logic established during training to output a predicted label. The classifier model produced in Phase 1 becomes the static engine that processes every new input in Phase 2. To understand how the computer actually finds those patterns, we have to look at the 3 pillars of the learning algorithm: representation, evaluation, and optimization. Representation defines the hypothesis space. This is the set of all possible models the algorithm can choose from. If we are using a linear model, the hypothesis space is every possible straight line that could divide the data points on a graph. Evaluation is the second pillar. The system needs a way to judge its progress. It calculates its error rate by comparing its current predictions against the performance metric, P. Finally, optimization is the process of improvement. The algorithm mathematically adjusts its internal parameters, shifting the line, to minimize the error it found during evaluation. In this context, learning is the mathematical search for the most accurate model within a defined hypothesis space. For years, the primary bottleneck in this field was feature engineering. A human had to manually decide which traits of an image or a sound were worth measuring. This traditional workflow relies on fixed, handcrafted feature grids. Data scientists had to build these filters manually before the machine learning classifier could even begin its work. Deep learning was designed to eliminate that manual step. Here, a neural network performs learnable convolutions. Instead of a human defining the features, the network identifies the most relevant patterns in the data itself and passes them to the classifier. This final evolution creates an end-to-end model. The neural network handles the entire pipeline, from raw input to final classification within a single system. Deep learning integrates the steps of feature extraction and classification into a single automated pipeline. Understanding the architecture is only half the story. As this lifecycle shows, a model's utility is ultimately defined by the data environment it lives in. Supervised learning is used when we have a history of labeled data. We know what spam looks like or what a loan default looks like, and we train the model to find those specific targets. But in many real-world scenarios, data is unstructured. We have the information, but we don't have the labels to tell the machine what that information means. This is where unsupervised learning comes in. Instead of looking for a specific target, clustering algorithms analyze the data to find inherent similarities and group them accordingly. A supermarket might use this to analyze shopping baskets. Without any prior labels, the algorithm can group customers by buying patterns, uncovering specific consumer segments that were previously invisible. Supervised learning maps known historical patterns, while unsupervised learning uncovers new, hidden structures within a dataset. There is a third environment, one where there is no historical data at all. Reinforcement learning is the study of agents that learn through direct interaction. There's no training set, only a reward function providing feedback based on the agent's actions. When a robot navigates an unknown room, it learns through trial and error, receiving rewards for reaching goals and penalties for collisions. By continuously updating the probability of its successful actions, the agent builds a map of the environment over time, optimizing its path through a world it has never seen before. From supervised classifiers to neural networks and reinforcement agents, these tools represent a shift in how we solve problems. Across all paradigms, machine learning is the mechanism for translating raw experience into a predictive mathematical model.